Let's talk about drive systems in coaxial helicopters. And specifically, we'll talk about the drive system for this fictional coaxial helicopter that I started designing with help from my YouTube subscribers in January of 26. This is the second video in this series, and I'm planning two more after this one. I'd like to get into the performance of coaxials in one of those future videos, but since we're talking about drive systems today, it's worth mentioning that size, weight, cost, and complexity of both drive systems and flight controls is one of the things that has historically kept customers away from interest in coaxial designs. Although maybe the small aircraft market in 2026 seems to show some renewed interest in coaxial helicopters. The design goal of a coaxial drive system is pretty straightforward. There's a clockwise driven upper rotor and a counterclockwise driven lower rotor, and we have to get the drive power from the power plant to each of these. There are several ways to do this, but here's what I came up with. I started with the spur gear to drive the lower counterclockwise rotor mast, then added another spur gear to drive the upper clockwise mast, then drive pinions for each of the larger gears on a common drive shaft so that they rotate at the same speed. By now you should notice the difference in pitch diameters of the upper and lower gears, and different diameters means the lower drive pinion doesn't mesh with the lower spur gear. Obviously this is a problem, but we can solve it by adding this idle gear that also serves to reverse the direction of the lower spur gear. Now when I rotate the input pinions in the same direction, because they're connected to the same drive shaft, the large spur gears rotate in opposite directions. And that difference in pitch diameters was necessary to get the clearance needed here. Hey, just as a by the way, if you'd like to 3D print a version of this, I have a file on my Buy Me a Coffee page. That's buymeacoffee.com/bzig. It's not exactly the same as what I'm showing in this coaxial design, but it's the same concept. Now, the different pitch diameters needed to get the clearance in the gears is a result of using the same tooth count in the upper and lower gears, but different gear modules. The math here is that the pitch diameter is equal to the module multiplied by the tooth count. The upper counterclockwise set are module 5.25 with a 43 tooth gear and a 19 tooth pinion. The lower clockwise gears are module 4.75, also with the 43 tooth gear. Both the drive pinion and the idle gear are 19 tooth gears. The final step in this drivetrain is to add a 90-degree spiral bevel gear that serves two purposes. It further reduces the rotation speed from the engine, and it changes the drive direction 90 degrees so that the engine can be mounted horizontally. Earlier I'd said that there are other ways to achieve counter-rotation. Most airplane counter-rotating propellers use what's called a differential planetary. Typically, in a planetary gear, you would drive the sun gear and then constrain either the planet carrier or the ring gear to get either a forward or a reverse gear. For example, if you fix the ring gear, the planet carrier is a forward gear. It turns in the same direction as the sun gear input. And if you fix the planet carrier, the ring becomes a reverse gear. It turns opposite the direction of the sun gear input. But if you fix neither the ring nor the carrier, they will counter-rotate. However, they won't counter-rotate at the same RPM. The rotation speed of the ring and carrier is driven by how much drag each propeller creates. The rotation speed can be made to be nearly 1-to-1 through propeller governing, but it won't be exactly 1-to-1. And this brings up an obvious question, which is it necessary for these two rotors to rotate at the same speed? I started this design with the preconceived notion that synchronized counter-rotation was a design requirement. I initially thought that cyclic control, the way I implemented it with upper and lower swash plates, had to be exactly 180 degrees out of phase between the upper and lower rotors. This led me to the design decision to use this reversing idle gear transmission. The key difference from the planetary design is that the reversing idle gear locks counter-rotation into a 1-to-1 synchronized relationship. But as it turns out, this constraint wasn't necessary. Cyclic control does need to be 180 out of phase, but what matters is the blade azimuth and not the relationship to the other blade. What's playing on the screen now is a 3-to-1 difference in rotation speed. The upper rotor is turning 3 times faster than the lower. An advantage of the 1-to-1 design is that you'd have consistent blade-to-blade clearance due to flapping in response to cyclic inputs, but this would only be true in a hover. So it's not much of an advantage. A possible disadvantage of the planetary design is that you'd have a rotating blade passing location, and this would be an annoyance to anybody flying in the aircraft. Fixed-wing turboprops have propeller synchrophasers to avoid this, but this is a noise, vibration, and harshness issue and otherwise not necessarily a bad design. And there's likely a performance benefit to be had from variable speed rotation, but I picked a gearbox with a synchronized rotation, so let's get back to that. The overall gear reduction of this gearbox is 4.41 to 1. The first reduction stage happens at the spiral bevel gears. The pinion gear has 19 teeth and the larger gear has 37 teeth, so this first stage reduction is 37 to 19 or about 1.9 to 1. Then the second stage reduction happens at the spur gears. Each of these has a 19-tooth pinion and a 43-tooth gear. This is a 43 to 19 reduction, or about 2.3 to 1. And combined, that's a total 4.41 to 1 reduction. This is a small helicopter. The main rotor diameter is about 7 meters, so I selected this amount of gear reduction based on a piston engine that would be appropriate for this size aircraft. The Lycoming engines typically used in small helicopters operate at 2,500 RPM, so a gear reduction of 4.41 to 1 means the main rotor will operate at 567 RPM. And this results in a worst-case tip Mach number of 0.9. The parameters that I built into this were a forward flight speed of 140 knots at a cold day temperature of negative 25 C. When it comes to selecting the rotor RPM, the Mach number at the blade tip is the key driver of that design parameter. Tip Mach number is the ratio of the airspeed at the rotor tip to the local speed of sound. As a design goal, the rotor tip Mach number must stay subsonic. That is, the Mach number must be less than 1. When wings go supersonic, there's a rearward shift in the aerodynamic center. Helicopter rotors, unlike airplane wings, don't have a tail, so they have no way to deal with the supersonic nose-down pitching moment. This and transonic drag rise are the compelling reasons to keep helicopter blade tip Mach numbers less than 1. The last drive system design goal that we'll talk about today is the requirement for helicopters to glide without engine power to a safe landing. This is called auto-rotation, and it happens when the pilot lowers the collective. This tilts the blade's aerodynamic force vector forward and motivates blade rotation without engine power. And when I said auto-rotation is a requirement, I'm aware of some small helicopters, one example is the Nolan Brothers H-51, that don't have auto-rotation capability. And neither do the next generation of vertical lift aircraft. The thought with these newer aircraft is that the reliability of multiple electric motors will eliminate the need to ever auto-rotate. But in aircraft that can auto-rotate, when the force vector tilts forward, you don't need the engine to power the blades. Instead, the air coming up through the bottom of the rotor disc sustains rotation. But an unpowered engine puts drag into the drive system that can slow or even stop auto-rotation. So in order to enable a successful auto-rotation, it's first necessary to decouple the engine and the high-speed portions of the drive system. That's the purpose of the sprag clutch. For this design, I put the sprag clutch here. At this location, it will decouple the engine and the 2 spiral bevel gears from an auto-rotating aircraft. But when it decouples, the spur gears will continue to rotate, but they're now powered by the rotor instead of the engine. And this is goodness. Even though these gears no longer have a role in transferring power, they must stay engaged in order to synchronize the 2 rotors. Sprag clutches are completely automatic. The geometry of the sprags is such that this dimension is longer than this dimension. Under engine power, the outer race is driven clockwise and the sprags are wedged into position. This transfers drive power to the inner race and then to the rest of the rotor system. But when the engine fails, this drive shaft becomes driving instead of driven, and it's now the inner race that rotates clockwise, and the sprags rotate out of the way, out of that wedged position. This is the freewheeling position, and this means that drive power cannot be transferred from the rotor to the engine. Hey, that's all I have for today. If there's continued interest, I may follow up with a video on the flight control system, discussing the two swash plates and the differential collective control, and then possibly another video showing the rotor hubs and the coupled motions that are usually desirable in a coaxial helicopter. In support of that, I modeled this separate hub that has 45 degrees of delta 3, and this will give a 1-to-1 flap to pitch coupled response. I'm also having some fun right now getting into the gimbaled rotor hubs that are used in the V-22 Osprey and the Augusta 609. But as always, if there's something else you'd like to see, please try to get a discussion going in the comments and we'll see where that leads. See you on the next video.